You're made of them. Everything you've ever touched is held together by them. And yet, after 100 years of staring straight at the electron, physics still cannot tell you what one actually is. A particle smaller than zero, a wave in two places at once, something that walks through walls, knows what its twin is doing across the galaxy, and rewrites its own behavior the moment you look. Tonight, we follow the electron into territory that has broken the smartest minds alive. Subscribe and stay close. What's coming next will change how you see reality. Settle in. Don't fight it. Let it pull you under. You are reading these words because of the electron. The light hitting your eyes, the signal in your nerves, the chemistry of every breath you take, all of it runs on a single particle that nobody on Earth fully understands. Think about that for a moment. The electron is the most studied object in the history of science. We have measured it to a precision finer than any other thing in nature. We build entire civilizations on top of it. Every computer, every phone, every hospital scanner, every power grid, they all depend on us being able to push electrons around with surgical accuracy. And we are very good at pushing them around. Engineers can guide trillions of them through a microchip the size of a fingernail, without a single one stepping out of line. Doctors use them to image the inside of your skull. Physicists smash them together at nearly the speed of light and watch what falls out. So you would assume, after all of that, scientists know exactly what an electron is. They do not. When you ask a physicist to describe one, really describe it, not just calculate what it does, the conversation falls apart fast. They will tell you it has no size. They will tell you it has no shape. They will tell you it has a spin, but nothing is actually spinning. They will tell you it is a particle, except when it isn't, and then it is a wave, except when it isn't that either. Every time scientists thought they had pinned the electron down, the electron quietly broke another rule. It went through walls it shouldn't have crossed. It reached zero size and refused to explode the way the math said it should. It coordinated with other electrons across vast distances, with no signal between them. It rotated 360 degrees and came back wrong, like a coin flipped twice that landed on a third side. And here is the part that makes physicists lose sleep. The electron is not some exotic particle hiding deep inside a particle accelerator. It is not rare. It is not subtle. There are roughly 10 octillion of them inside your body right now. That is a 1, followed by 28 zeros. Every atom in every star, every drop of water in every ocean, every cell of every living thing leans on this particle to exist. The thing breaking the laws of physics is also the thing holding the universe together. For 100 years, the smartest people on Earth have been chasing it. They have built machines that cost billions of dollars. They have written equations that predict its behavior to 14 decimal places, the most accurate predictions humanity has ever made about anything. Those predictions work beautifully. They power the modern world, but predicting what something does is very different from understanding what it is. A weather forecaster can predict rain without knowing why water exists. Physics is in a similar position with the electron. We can tell you with terrifying precision what it will do. We cannot tell you why it does it. In the chapters ahead, you are going to meet an electron that walks through solid barriers, splits itself across two paths at once, and freezes scientists with results so strange they have to be checked 1,000 times before anyone believes them. The first stop is the simplest experiment in modern physics. 2 narrow slits, 1 particle, and a result that should not be possible. In a quiet laboratory, a physicist sets up the simplest experiment you can imagine. A small electron gun on one side, a wall with 2 narrow slits cut into it, a detector screen on the far side. That is all. Send a steady stream of electrons at the wall. Some will hit the wall and stop. Others will pass through one of the 2 slits and land on the detector behind. Common sense says the result should be straightforward. 2 bright lines on the detector, lined up directly behind the 2 openings, like spray paint hitting a wall through a stencil. That is what classical physics demands. Particles fly in straight lines. A particle goes through slit 1, or it goes through slit 2. There is no third option. The physicists turn on the gun. The electrons stream out. The detector lights up. There are no 2 lines. There is a striped pattern, bright bands and dark bands, alternating across the screen. like ripples spreading from two stones dropped in a pond and meeting in the middle. The electrons did not behave like tiny bullets. They behaved like waves that overlapped and interfered with each other, brightening some places and cancelling out others. So the physicists try something cleverer. They slow the gun down to a crawl, one electron at a time, a single particle, fired alone with no other electrons anywhere near it. There is nothing for it to interfere with. It must. They fire one. A single dot appears on the detector. They fire another dot. Somewhere else. Hours pass. Thousands of single electrons, fired one by one, each one entirely alone in the apparatus. The dots accumulate on the screen, building up slowly, and the pattern that forms is the striped pattern, the interference bands. Each individual electron, fired alone, somehow knew about both slits. Each one passed through the apparatus as if it were a wave spread across both openings at once, interfering with itself, and then collapsed into a single dot when it hit the screen. A single particle cannot go through two slits at the same time, except, apparently, it can. The physicist Richard Feynman called this the only mystery of quantum mechanics, and said that nobody could give you a deeper explanation than simply describing what happens. He spent his life on this problem. He never solved it. Wikipedia. The experiment has been repeated for over a century with cleaner equipment, colder labs, and more sensitive detectors. The result is always the same. It has been performed with molecules made of 2,000 atoms, objects 10,000 times bigger than an electron, and even then, the striped pattern appears. Whatever the electron is doing, larger objects can do it too. Wikipedia. A single particle behaves like a wave passing through both openings, then snaps into a single point at the moment it is detected. The wave is real enough to interfere with itself. The point is real enough to leave a mark. Now, the physicists ask the obvious question. If the electron is going through both slits, can we catch it in the act? Can we put a tiny detector at one of the slits and actually watch which one it chooses? They try. They build an instrument so sensitive it can register a single electron passing through a single opening without blocking the electron's path. They run the experiment again. They watch the slits. And the moment they do, something even stranger happens. The pattern on the back screen changes completely. The detector is on. The physicists are watching the slits. Every electron is fired one at a time, and now, for each one, the equipment registers a tiny click telling them which slit it passed through. Slit 1, slit 2, slit 1, slit 2. Each electron makes its choice. Each one is recorded. The dots accumulate on the back screen. The striped pattern is gone. In its place, there are two simple bright bands lined up directly behind the two openings. Exactly the result classical physics predicted in the first place. The electrons are now behaving like ordinary particles, like tiny pellets fired through holes, hitting the wall in two clean stripes. The physicists turn the slit detector off. Just turn it off. Nothing else changes. Same gun, same wall, same back screen, same single electrons fired one at a time. The striped pattern returns. Wave behavior, interference, the works. Turn the watcher back on, two stripes again. Particle behavior, off, stripes vanish, ripples return. This is not a glitch. This has been verified thousands of times in laboratories around the world. The act of measuring which slit an electron goes through is enough to change what the electron does. Watch it, and it acts like a particle. Look away, and it acts like a wave. Try to wrap your head around what that means. A single electron is fired toward the wall. Whether it behaves like a spread-out wave passing through both slits, or like a tiny ball passing through one, depends on whether or not someone is paying attention. The first thing physicists tried, naturally, was to blame the equipment. Maybe the slit detector was nudging the electron somehow. Maybe the act of measuring physically jostled it. So they made gentler detectors. They used softer light. They shielded the experiment from every form of interference they could think of. It made no difference. As long as information about which slit was used could in principle be obtained, the wave pattern collapsed. Even when the measuring device was placed after the electron had already passed through the slits, even when the choice to measure was made at the very last moment, the electron's behavior changed. This last version is called a delayed choice experiment. The electron is already on its way to the back screen. The decision to look or not to look is made after the electron has crossed the slits, and somehow the electron behaves as if it knew from the start what was going to happen later. The implications are deeply uncomfortable. It looks as if the electron does not commit to being a particle or a wave until it has to. It looks as if reality itself is somehow paused, undecided, waiting on a measurement. Physicists do not like words like decided or knew. Particles are not supposed to know things. So they have spent a century trying to find an explanation that does not require the universe to behave like a mind reader. There are several proposed answers. One says the electron exists in a kind of probability fog until it is measured, and the measurement forces it to become real in one location. Another says every possible outcome happens in separate parallel universes, and we only see the one we ended up in. Another says the future and the past are tangled together in ways our equations are barely beginning to capture. None of these has been proven. The experiment keeps working. The watcher keeps mattering. Whatever an electron is, it is not the kind of thing you can simply stare at without changing. Most things in the universe are one thing. A rock is a rock. A wave on the ocean is a wave. The wind is the wind. They have a single nature, and they keep it. The electron does not. Hold up a magnifying glass to one and try to describe it, and you will find yourself trapped between two completely different vocabularies. Sometimes the electron is a particle, a single point, hitting a single spot, leaving a single mark. Sometimes it is a wave, spread out across space, oscillating, capable of overlapping itself and creating patterns of bright and dark. It is both. It is neither. It is something we do not have a word for. This is called wave-particle duality, and it is one of the most accepted, most experimentally verified, and most genuinely uncomfortable ideas in modern physics. The electron is not a wave that pretends to be a particle. It is not a particle that pretends to be a wave. It is whatever it is, and our two human concepts each capture part of the picture and miss the rest. Here is a useful comparison. Imagine a creature that lives in two dimensions, a flat being on a flat sheet of paper. One day a sphere passes through its world. The flat creature cannot see a sphere. It can only see slices. First a tiny dot, then a growing circle, then a shrinking circle, then nothing. To the flat creature, the sphere is a series of unrelated shapes. To us, it is one simple object that the flat creature lacks the dimensions to perceive. Physicists suspect the electron is something like that. It is one thing. We are the flat beings. Our concepts of particle and wave are the slices. The electron itself is whatever shape connects them, and that shape lives in a space our minds did not evolve to picture. The duality runs deeper than just behavior. It is built into the math. Every electron in the universe is described by something called a wave function, a quantity that spreads out through space and tells you the probability of finding the electron in any given spot. The wave function is a wave in every meaningful sense. It can rise and fall, it can interfere with itself, it can be split and recombined. But you never measure the wave function directly, you measure the electron. And when you do, you always find it in one place, like a particle. The wave seems to collapse the moment you look, leaving a single dot behind. So which one is real? The wave that spreads through the apparatus? Or the dot that lands on the screen? Both. Neither. The honest answer is that physics has no idea. The wave function predicts the dots with perfect accuracy. We use it to design lasers, microscopes, and quantum computers. It works, but asking what the wave function physically is, whether it is a real ripple in some unseen medium, or just a mathematical bookkeeping tool that has no existence outside our equations, gets you a different answer from every physicist you ask. Some say the wave is real and the particle is an illusion of measurement. Some say the particle is real and the wave is just a description of our ignorance. Some say both are real and our universe is one branch of a tree where every other possibility is also playing out. Somewhere we cannot see, the electron does not care which interpretation you prefer. It keeps doing what it does, and in the next chapter, you will see one of the strangest things it does, a kind of motion that requires you to turn it twice around before it remembers who it was. Pick up a coffee cup, turn it 360 degrees. It is back where it started. This is the most basic fact about rotation in our universe. One full turn returns you to the beginning. Anything else would feel insane. Now imagine an object that, after being rotated 360 degrees, is somehow not back where it started. An object that needs a second full turn, 720 degrees, 2 complete revolutions, before it is truly home. That object is the electron. And this is not a metaphor. It is a measured, experimentally confirmed property of every electron in existence. In quantum mechanics, the electron is described mathematically by something called a spinor. A spinor is a strange cousin of an ordinary vector. Rotating a spinor by 360 degrees does not bring it back to the same quantum state, but to the state with the opposite quantum phase. To return the particle to its exact original state, one needs a 720-degree rotation. Read that again. Rotate an electron once around, and it has not returned to itself. It has flipped. Rotate it a second full turn, and only then does it come home. If this seems impossible to picture, that is because nothing in your everyday experience behaves this way. There is one trick that comes close, though. It is called the belt trick, or the Dirac belt trick, after the physicist who first noticed it. Take a belt, hold one end fixed in your left hand. With your right hand, give the other end a single full twist, 360 degrees. Now the belt has a twist in it. You cannot remove that twist by sliding the belt around without rotating the ends. It is stuck. Now, holding the ends fixed, give the right end a second full twist in the same direction. 720 degrees total. The belt now has 2 twists. And here is the strange part. Without rotating either end, you can pass the loops of the belt over and under in a clever motion, and the twists cancel out. The belt becomes flat again. A double twist can. The universe seems to know the difference between them, and electrons live in this same kind of mathematics. The effect is not just theoretical, it has been measured directly. Physicists can take a beam of electrons, split it into 2 paths, rotate the electrons along one path with a magnetic field, and recombine the beams. When the rotation is 360 degrees, the recombined beam shows a clear sign that the rotated electrons are out of step with the unrotated ones, like 2 singers in opposing keys. When the rotation is 720 degrees, the 2 beams sync back up perfectly. The universe genuinely treats one full rotation as not enough. Because this property, being a spinor instead of an ordinary object, is not some quirky decoration, it is the reason matter can exist in the first place. Spinors are the mathematical category that includes electrons, protons, neutrons, and every fundamental building block of ordinary matter. Their bizarre rotational behavior is tied directly to a rule that prevents 2 electrons from sharing the same state, which in turn is the reason atoms have structure, the reason chemistry works, and the reason your body does not collapse into a single point. If electrons were ordinary objects that returned home after 360 degrees, every atom in your body would unravel. The chair you are sitting on would not hold. Stars would not shine. A geometry no human can directly visualize is the only thing standing between you and oblivion, and that geometry comes built into a property of the electron called spin, a property that is not really spinning at all. The word spin is one of the most misleading terms in physics. Every electron has a property called spin. The number is exact, the same for every electron in the universe. 1/2 in the units physicists use. It produces measurable magnetic effects. It governs whole branches of chemistry and engineering. Spin is real. Nothing is actually spinning. When physicists first discovered that electrons behaved like tiny magnets, the obvious explanation was that they were rotating. A rotating ball of charge produces a magnetic field. Calculate how fast an electron would have to rotate to produce its measured magnetism, and you get a number that is staggering. The surface of the electron would have to be moving many times faster than the speed of light. Faster than light is not allowed, not by a small margin, by a huge one. Worse, the electron has no surface, it has no measurable size at all. There is nothing to spin. It is angular momentum, the same quantity a spinning top has, but built into the electron from the moment it exists, with no rotation behind it. It is as if the universe handed every electron a fixed amount of twist as a starting condition, and that twist behaves in every way like rotation, except that nothing is actually rotating. The discoverer of this property, Wolfgang Pauli, was so disturbed by it that he gave it the most polite name he could find. He called it a classical, non-describable two-valuedness. Translated from physics into English, that means there are two settings, we have no everyday picture of what they are, and please stop asking us to explain them in normal language. Two settings, up or down. That is all an electron's spin can ever be when you measure it. There is no halfway. You cannot find an electron with its spin pointed sideways or at a 30-degree angle. Every measurement returns either up or down, perfectly cleanly, with no in-between. But here is the strange part. Before you measure, the electron does not have a definite up or down. It is in a kind of mixture, a superposition of both possibilities at once. Only the act of measurement forces it to pick. Measure along a different axis, and the rules apply again. Pure up or pure down, with no in-between, even though the axis is now pointing somewhere else entirely. This sounds like it should produce contradictions, and in a sense it does. There is a famous experiment where you measure an electron's spin in one direction, get a definite answer, then measure it in a perpendicular direction. The second measurement scrambles the first. Measure in the original direction again, and the result is now random. The electron cannot remember what its spin was, because in the new direction, it never was anything definite. A property that exists only when you look at it, a rotation that is not rotating. Two settings that can also somehow be both at once. Spin is the universe's way of telling us that some things in nature simply do not have classical pictures. There is no little ball, there is no little arrow, there is nothing solid we can imagine that would behave the way spin behaves. The mathematics works, the predictions are exact, and the behind-the-scenes picture is a blank. This is the price of being honest about quantum mechanics. The math gives you the right answer to 14 decimal places. The story you tell yourself about what is happening is yours to invent, and probably wrong. And spin is not even the strangest thing about the electron's body. Ask physicists how big an electron actually is, and the answer becomes something close to a paradox. Hold up a finger. Imagine zooming in on the tip of it, deeper and deeper, past the cells, past the molecules, past the atoms, until you are looking at a single electron. How small is it? The honest answer is that it has no size at all. The standard model of particle physics, the most successful theory of matter ever built, treats the electron as a point. Not a small thing, not a tiny ball, a literal mathematical point with zero radius, zero diameter, zero volume. This is not a placeholder for a number physicists have not measured yet. They have measured. Every experiment ever performed on the electron has come back consistent with it being exactly that, a point with no detectable internal structure. A query about the size of the electron yields the answer that it is a point particle with a point charge and no spatial extent. The electron radius is smaller than 10 to the minus 22 meters, and every attempt to find a smaller boundary has failed. Arcsev. To put that in perspective, 10 to the minus 22 meters is roughly 100 million times smaller than a single proton, which is itself already absurdly tiny. If you blew up a proton to the size of a city, the electron would still be smaller than a grain of sand. And that is only the upper limit of what we have failed to detect. The electron might genuinely be a point with no size at all. The problem is that this should be impossible. An electron carries a negative electric charge. Charges create electric fields. Squeeze any amount of charge into a smaller and smaller region, and the field around it grows stronger and stronger. The energy stored in that field grows too. Experimentally, the electron shows itself as a point particle without size. This is devastating because the energy content of the electric field is infinite. For a point particle, Arcsev, infinite energy. By the most basic equations of electromagnetism, an electron compressed to a single point should have infinite mass, infinite energy, and should be the most violent thing in the universe. It is not. An electron has a small, finite mass. It sits politely in atoms. It does not rip the cosmos apart. The math says it should explode reality. Reality somehow does not get the message. For nearly a century, this has been one of the deepest open wounds in physics. It is so embarrassing that physicists have a term for the procedure they use to deal with it. They call it renormalization. The technique amounts to subtracting infinity from infinity to get a finite answer, in a careful and consistent way that, by some miracle, agrees with experiment to staggering precision. Renormalization works. It produces predictions accurate to 14 decimal places. It powers entire branches of modern physics, and it deeply bothered the physicists who invented it. Paul Dirac, one of the founders of quantum theory, called it ugly. Richard Feynman called it a dippy process. They suspected, both of them, that an answer this strange was hiding a deeper truth nobody had yet uncovered. That truth might be that the electron is not really a point, but a tiny, finite, structured object, whose details we cannot yet probe. Or it might be that our concept of point itself breaks down at this scale, and the electron is something neither point-like nor extended, but something else entirely. Either way, every electron in your body is a contradiction the universe has somehow swallowed and digested. Zero size, real charge, finite mass, math that screams at the edges, and answers that come out clean anyway. The universe is hiding something. And it gets worse, because that infinite energy problem is just the beginning of the trouble. Take the electron's infinite energy problem and try to write it down properly. Try to use it in a calculation. The equations explode in your face. Every reasonable attempt to compute what an electron should do, using straightforward physics, produces infinity. Not just one infinity, layer upon layer of them. The mass comes out infinite. The charge comes out infinite. The energy comes out infinite. Run the math honestly, and the most ordinary particle in the universe becomes a fountain of impossible numbers. For the first half of the 20th century, this was considered a sign that quantum theory was broken. Some of the smartest minds alive, Einstein, Bohr, Heisenberg, Dirac, could not see how a theory producing infinities could be the right description of nature. Either the math was wrong, or there was something deeply missing from our picture of reality. A solution arrived in the late 1940s, and it was so strange that even its inventors did not fully trust it. The technique is called renormalization, and the idea, stripped of its technical machinery, is this: the infinities show up because we are pretending the electron is a bare, lonely particle sitting in empty space. But the universe is not empty. According to quantum theory, what looks like empty space is actually a seething ocean of particles popping in and out of existence. Pairs of electrons and their antimatter twins, photons, all manner of ghostly visitors, each one appearing for a brief moment and vanishing. An electron is never alone. It is always surrounded by a swirling cloud of these temporary visitors. The cloud shields it. It changes the way the electron looks to anything probing it from outside. The mass and charge that we measure with our instruments are not the bare electron at all. They are the electron plus its cloud, the whole package as observed from the outside. The bare electron, by itself, might genuinely have infinite mass. The cloud around it might genuinely have negative infinite mass. The two together, the only thing we can ever measure, work out to a small, finite, sensible number. You subtract infinity from infinity. You do it carefully, with strict mathematical rules. And the answer that falls out predicts the behavior of the electron more precisely than any prediction in the history of science. The wobble of an electron in a magnetic field, its anomalous magnetic moment, has been calculated using this method to 14 decimal places. It has been measured in the laboratory to 14 decimal places. The two agree. This is the most accurate match between theory and experiment that humans have ever achieved, in any field. And it relies on subtracting infinity from infinity. The physicists who developed this technique knew there was something deeply wrong with it. Paul Dirac, who spent decades trying to find a clean alternative, put it bluntly. He said the rules of the game were ridiculous, that physicists had not solved the problem, they had simply learned to sweep it under the rug in a way that worked. Richard Feynman, one of the people who built the framework, called it a dippy process and admitted that the procedure was not mathematically legitimate. He still used it. Everyone uses it. There is nothing better. What renormalization is telling us between the lines is that our equations are saying something real about the electron, its surrounding cloud of virtual particles, the structure of the vacuum itself, but our way of writing those equations is too crude. We are catching glimpses of a deeper layer of reality through math that screams every time we get too close. For now, the trick works, and physics moves on. But it moves on with a quiet acknowledgement that the foundation it stands on is patched together with mathematical duct tape. The truly disturbing part is that this is one of the milder rules the electron breaks, because now we have to talk about how an electron walks straight through a wall. In the world you live in, walls work. Roll a ball at a brick wall hard enough, and it bounces off. Roll it gently and it stops. Roll it any way you like, the ball does not pass through the wall. There is too much energy in the wall, too little in the ball, and the geometry is decided. Electrons do not follow this rule. If you place an electron next to a barrier, an energy barrier, the quantum equivalent of a wall, and the electron does not have enough energy to climb over the barrier, classical physics says the electron stops. Period. It cannot get to the other side. But quantum mechanics says something else. There is a small chance, a real and calculable chance, that the electron will simply appear on the other side of the wall. It does not climb over. It does not break through. It vanishes from one side and reappears on the other, as if the wall were not there at all. This is called quantum tunneling, and it is not a theoretical curiosity. It is one of the most experimentally verified phenomena in all of science. Here is how strange it is. The electron does not have the energy to be inside the barrier. According to classical physics, the moment it tries to enter the wall, it should be stopped, cold. It would need to borrow energy from somewhere just to exist in there, and yet the electron's wave function, the wave that describes where it might be found, extends a small distance into the wall and beyond. If the wall is thin enough, the wave continues out the other side. Measure the electron, and there is a finite chance you find it on the far side, with all of its original energy intact, as if it had paid no toll at the gate. The thinner the barrier, the higher the odds. The thicker the barrier, the lower. But the chance is never exactly zero, no matter how solid the wall looks. This is not a niche effect happening only in laboratories. Quantum tunneling is the reason the sun shines. This phenomenon is the principle by which semiconductors, the core components of smartphones and computers, operate, and is also essential for nuclear fusion, the process that produces light and energy in the sun. Science daily, inside the sun's core, hydrogen nuclei need to slam into each other hard enough to fuse, releasing the energy that lights up our entire solar system. The temperatures and pressures are immense, and yet by the strict rules of classical physics, the nuclei still do not have quite enough energy to overcome the electrical repulsion between them. They should bounce off every single time. The sun should not shine. But quantum tunneling lets a small fraction of those collisions succeed. The nuclei do not have the energy to climb the barrier between them, so they tunnel through it. That trickle of impossible fusions adds up, multiplied across uncountable particles, into the steady blaze that has warmed Earth for 4 billion years. Tunneling powers your microchips. Every transistor in every phone, every laptop, every car relies on electrons crossing barriers that classical physics says are impassable. Without tunneling, there is no modern computer. Without tunneling, there is no sunlight. Without tunneling, life on Earth is impossible. A particle that walks through walls is the engine of civilization and the engine of stars. We have built our world on top of an electron's ability to be where it should not be. For 100 years, physicists could predict the outcome of tunneling without having any idea what the electron was actually doing inside the wall. The entrance and exit were known. The middle was a black box, and in 2025, an experiment finally cracked the box open. What scientists saw inside was even stranger than the tunneling itself. Until 2025, no one had ever seen what an electron does in the middle of a tunneling event. Physicists could prepare the electron, fire it at a barrier, and detect it on the other side. The act of crossing was instantaneous, hidden, untouchable. The middle of the tunnel was a place you could not photograph. A team at the Pohang University of Science and Technology in South Korea, working with physicists at the Max Planck Institute for Nuclear Physics in Germany, decided to try anyway. They built an experiment with laser pulses so short and so precise that they could freeze a single instant of a tunneling event, the way a high-speed camera freezes the instant a water drop hits a surface. They watched. What they saw should not have been possible. For the first time ever, scientists watched electrons perform a bizarre quantum feat, tunneling through atomic barriers by not just slipping through, but doubling back and slamming into the nucleus mid-tunnel. Read that carefully. The electron does not just travel from one side of the barrier to the other. Halfway through, it reverses. It loops backward. It collides with the very atomic nucleus it was supposed to be escaping. Then it continues on its way, exits the barrier, and arrives on the other side as if nothing strange had happened. The team confirmed this through repeated experiments. They were not seeing a fluke. They were seeing a fundamental hidden feature of how tunneling actually works. A feature that had been quietly invisible to physics for over a century. The professor leading the work explained it simply. Until now, scientists knew the entrance and the exit of the tunnel. The middle had stayed a mystery. Now we have a glimpse, and the middle does not behave the way anyone expected. There is no classical analogy for this. Imagine a ghost trying to walk through a wall. Halfway through, the ghost turns around, runs back, smashes into the front of the wall, then resumes its journey forward and emerges on the other side. And despite all this, the entire trip took less time than a normal walk. That is something close to what an electron does inside a tunneling barrier. Why does the electron do this? Nobody knows for sure. The mathematics of quantum mechanics produced this prediction implicitly, hidden inside the equations, but no one had pulled it out and tested it directly until the South Korean and German teams built an apparatus precise enough to catch it. The implications run deep. Quantum tunneling is not a niche effect. It is the engine of nuclear reactions, the foundation of semiconductors, and a key process in chemistry and biology. The discovery that the electron loops back and recollides during the tunneling event suggests that all of these processes have a hidden internal step we have been ignoring. The behavior of stars, the operation of computer chips, the way enzymes catalyze reactions inside living cells, every one of these might have an unseen layer of complexity tied to this unexpected backward loop. For now, the discovery is fresh enough that the full consequences are still being worked out. Physicists are running new experiments to confirm the result and to see what other hidden behaviors might be lurking inside other quantum processes. There is a sense in the field that the electron has just opened another door no one had noticed was there. There is a pattern forming. Every time we look closer at the electron, it does something stranger than before. It interferes with itself. It changes behavior under observation. It rotates in a geometry that takes 2 full turns to complete. It walks through walls. It loops back inside those walls and crashes into nuclei. None of these are things a sensible particle should be capable of. And the next strange property is the one Werner Heisenberg discovered in 1927. The rule that there are simply some questions about an electron the universe will not answer. In a sensible universe, you can know 2 things about a moving object at the same time. You can know where it is. You can know how fast it is going. A speeding car has a position on the highway and a velocity on its speedometer, and there is no rule saying you cannot measure both. For an electron, there is exactly such a rule. In 1927, the German physicist Werner Heisenberg worked out what he called the uncertainty principle, and it is one of the most disturbing ideas in modern physics. The principle says that for any quantum object, certain pairs of properties form an unbreakable trade. The more precisely you measure one, the less precisely the other is even allowed to exist. Position and momentum are the most famous of these pairs. This is not a statement about how good your equipment is. It is not saying our instruments are too clumsy. It is saying that the electron itself does not have a definite position and a definite momentum at the same time. The universe, at the level of an electron, is forbidding the question. Pin down where an electron is very precisely, and its momentum becomes a complete blur. It could be moving fast in any direction. It could be standing nearly still. The information is simply not there to be found, because nature does not store both things at once. Loosen up on position, and momentum sharpens. Let the electron be roughly here, plus or minus a small region, and its speed becomes well defined. The trade is locked in. Multiplied together, the uncertainty in position and the uncertainty in momentum can never fall below a fixed minimum, set by Planck's constant, one of the deepest, most universal numbers in nature. This rule shapes everything about how electrons behave. It is the reason an electron in an atom does not crash into the nucleus. Classically, a negatively charged electron should spiral straight into the positively charged nucleus. Since opposite charges attract, the atom should collapse in less than a second. Atoms exist for billions of years. The reason is uncertainty. If the electron tried to fall all the way into the nucleus, its position would become incredibly well defined, pinned to a tiny region. The uncertainty principle would then force its momentum to become enormous. A huge momentum means a huge kinetic energy, which would push the electron right back out. The electron settles into a stable orbit, not because of any classical balance of forces, but because the universe will not allow it to be both perfectly localized and perfectly still. Every atom in your body is held together by this rule. Your hand is not collapsing into a black hole right now because the universe refuses to let it. The uncertainty principle goes further. It applies to many other pairs, not just position and momentum. Energy and time form another such pair. Pin down a moment in time, and the energy of any process during that instant becomes wildly uncertain. This is the loophole that allows the foam of virtual particles, the seething vacuum, the cloud around every electron. Particles can borrow energy from nothing for very short moments, exist briefly, and vanish before the universe catches them. Heisenberg's discovery was met with horror by some of the founders of physics. Einstein famously hated it. He spent years trying to design clever experiments to defeat the uncertainty principle, to find a way to measure both position and momentum precisely at the same time. Every attempt failed. Bohr would find the flaw in Einstein's reasoning, often within hours. The universe simply will not let you have both. The uncertainty principle is the wall that surrounds the quantum world. We can describe what is on the other side. We can predict what will happen. We just cannot ever know everything about it at once. And the next rule on the list is the one that explains why your hand does not pass through this device, why you do not fall through the floor, why anything has any shape at all. In 1925, the same physicist who later named spin a non-describable two-valuedness discovered a rule about electrons, so simple and so consequential that without it, the universe as we know it could not exist. The rule is called the Pauli exclusion principle, and it goes like this. No two electrons in the same system can ever occupy the same quantum state at the same time. That is the entire rule. It sounds dry. The consequences are everything you have ever seen. When physicists say quantum state, they mean the complete set of properties an electron has at a given moment: its energy level, its spin direction, its orbit around an atom, its precise quantum identity. Two electrons can be in the same atom, but they cannot share every single one of these properties. If two electrons happen to have the same energy level and the same orbit, then one must spin up and the other must spin down. Otherwise, the universe will not allow them to coexist. This refusal is absolute. It is not a preference. It is not a force. It is not something the electrons negotiate. It is built into the deepest mathematics of who they are. Two electrons in identical quantum states is a configuration that simply cannot exist. The universe has a hard ceiling on it. This rule alone explains the structure of the periodic table. Hydrogen, the simplest atom, has one electron in its lowest energy slot. Helium has two, both in the lowest slot, but one spinning up and the other down, the only way two electrons can share an orbit. By the time you get to lithium, the lowest slot is full. The third electron has nowhere to go in the bottom level, so it must climb to the next energy level up. And from that simple geometric promotion comes the entirely different chemistry of lithium versus helium. Every chemical element behaves the way it does because exclusion forces electrons into a stack. The first slot fills up, the second one starts. Each new layer brings new chemistry. Iron is iron, gold is gold, oxygen is oxygen, all because of how its electrons are stacked, layer by layer, none of them allowed to crowd into the same lowest place. If exclusion did not exist, every electron in every atom would dive straight to the lowest energy level, the way water flows to the bottom of a basin. Atoms would lose their structure. There would be no chemistry, no molecules, no biology. The universe would consist of a uniform soup of identical particles, all huddled at the bottom of the same well. You exist because electrons refuse to share. The principle goes further than chemistry. When matter is squeezed extremely hard, inside white dwarf stars for instance, or the cores of certain dying stars, the only thing that prevents the matter from collapsing under its own gravity is exclusion. The electrons inside cannot pile into the same state, so they push back against the squeeze with a pressure that has no classical equivalent. It is not heat. It is not magnetism. It is the universe's refusal to let two electrons be the same. This pressure is called electron degeneracy pressure, and it holds up white dwarfs against the weight of more than one solar mass of crushing material. When even degeneracy pressure cannot hold, the star collapses further into a neutron star. When even neutron pressure fails, you get a black hole. Exclusion is the last line of defense before gravity wins. It is, in some ways, the most important rule the electron obeys, and it leads directly to one of the most surprising consequences of quantum mechanics: the reason solid matter feels solid, the reason your hand does not pass through your desk. Knock on a table, hear the sound, feel the resistance. The table is solid. Your hand stops at its surface. Whatever is going on at the atomic level, the result up here is reassuringly firm. Now consider what an atom actually is. A tiny nucleus at the center, surrounded by electrons buzzing around in orbits that are, on the scale of the atom, vast and mostly empty. If you scaled an atom up so that the nucleus was the size of a marble, the nearest electron would be orbiting at roughly the distance of a football stadium. The atom is more than 99.9% empty space. Stack atoms together to make a table. The table is also more than 99.9% empty space. So is your hand. Two clouds of mostly nothing meeting at a surface, and somehow the encounter feels like solid, striking solid. Why? The naive answer is that the electrons in your hand and the electrons in the table repel each other electrically, like charges push apart. That is partly true, and it does contribute. But it is not the main reason solidity exists. Electrical repulsion between two clouds of electrons at large separations is not strong enough to explain why your hand stops as cleanly and firmly as it does. The deeper reason is exclusion. When you push your hand into the table, you are trying to force the electrons in your hand to share the same region of space and the same quantum states as the electrons in the table. The Pauli exclusion principle forbids it. Two electrons cannot occupy the same quantum state. As you push, the universe refuses more and more strongly. The electrons in your hand cannot enter the slots already occupied by the electrons in the table. The only way forward would be to bump those electrons into higher energy states, and bumping them there costs real energy that has to come from somewhere, namely from your muscles pushing. Your hand stops because the energetic cost of further intrusion becomes huge almost instantly. Solidity is not a force in any classical sense. It is the universe billing you for trying to violate a rule about how electrons share space. This is why a feather does not pass through a brick wall, even though both are made mostly of empty space. It is why your chair holds your weight. It is why the ground does not let you sink through it. The structure of every solid you have ever touched is held in place by the steadfast refusal of electrons to share quantum states. There is a striking thought experiment that makes this real. Imagine you could turn off the Pauli exclusion principle for 1 second, just for the electrons in your body. What would happen? Every electron in every atom of every cell would suddenly be free to slide into the lowest available energy state. Atoms would lose their orbital structure. Chemistry would collapse. Your body, the ground beneath you, the air around you, would all fold in on themselves in a fraction of a second. There would be no resistance, nothing to push back, no reason for any object to occupy any volume. Exclusion is the pressure that gives the world its shape. It is the ghost in the architecture, present in every solid surface you have ever felt. The remarkable thing is that this pressure is not generated by a force in the way gravity or electromagnetism are. There is no exchange of force-carrying particles, no field stretching between electrons and pushing them apart. Exclusion is not a force at all. It is a constraint, woven into the mathematics of how identical quantum particles are allowed to combine. It produces effects that look exactly like a force, but its nature is something more abstract, a rule of arrangement written into the fabric of reality. The universe holds itself up by saying no. And the next strangeness about electrons is the one Einstein hated, more than any other. The way two of them, once linked, can stay connected across a galaxy. Two electrons can be prepared in a way that ties them together quantum mechanically. The process is delicate. They have to be brought into contact under specific conditions, often by interacting through some shared origin, a particle decaying into them, an atom emitting them simultaneously, a careful laboratory setup forcing their states to combine. Once linked, they are entangled, and entanglement is unlike anything in ordinary physics. The two electrons no longer have separate identities. They share a single quantum state that describes both of them at once. Whatever you measure on one, you instantly know something about the other, no matter how far apart they are. Quantum entanglement means that aspects of one particle of an entangled pair depend on aspects of the other particle, no matter how far apart they are or what lies between them. Imagine the cleanest version. Two electrons are prepared so their total spin must add up to 0. Send one to a laboratory in New York, send the other to a laboratory on the Moon. Neither electron, on its own, has a defined spin. Each one is in a quantum mixture of up and down. If you measured them individually before the linking, you would get random results. A scientist in New York measures her electron. The result is up. Instantly, at the same moment by every measurement physicists can perform, the electron on the Moon becomes definitely down. Not probably down. Not most of the time down. Down every single time, perfectly correlated with the New York measurement, regardless of the distance between them. Run the experiment again. Both electrons are in the unmeasured mixture. New York measures down this time. The Moon's electron is up. Always opposite. Always correlated. Always instantaneous. For decades, the obvious explanation was that the two electrons must have agreed on their answers before they parted. They each carried a hidden instruction, up or down, locked in from the moment they were prepared. The randomness we saw was just our ignorance of the instructions. There was nothing spooky. Just unknown information. This was the explanation Einstein favored. It was tidy. It preserved the world he believed in, where things have definite properties whether or not you measure them, and where no signal can travel faster than light. He was wrong. Starting in the 1970s, physicists began running experiments designed specifically to test whether hidden instructions could explain entanglement. The experiments grew more sophisticated, more rigorous, more airtight, decade after decade. Every single one of them ruled out the hidden instruction picture. The correlations between entangled electrons are too strong to be explained by any preset agreement. The universe really does seem to be deciding the outcome at the moment of measurement, and the two particles really do share a single state, regardless of how far apart they are. In 2022, 3 physicists were awarded the Nobel Prize for the experiments that finally settled this question beyond any reasonable doubt. Their work confirmed what quantum mechanics had been quietly insisting for almost a century. Entanglement is real, hidden variables are not, and the consequences are working their way into the modern world. Entanglement is the foundation of quantum computing, where linked particles allow calculations no ordinary computer can perform. It powers experimental quantum communication systems, where eavesdropping is detectable because any measurement disturbs the link. Quantum entanglement has been mapped inside individual protons, where it occurs over incredibly short distances, less than 1/4,000,000th of a meter, and the sharing of information extends over the entire group of quarks and gluons inside. Entanglement is not just 2 electrons in a lab. It is built into the structure of matter itself. But the truly disturbing part of entanglement is not that it exists, it is what it implies about distance. The speed of light is the universe's strict rule. Nothing travels faster than it. Not signals, not energy, not information of any kind. This is the bedrock of Einstein's relativity, the law that has survived every test thrown at it for over 100 years, and entanglement appears to break it. When the New York physicist measures her electron and finds it spin up, the electron on the Moon becomes definitely spin down at the same moment. There is no delay for light to travel from the Earth to the Moon, which takes about 1¼ seconds. The correlation is instant. Whatever connection links the 2 electrons does not seem to care about distance at all. This is what made Einstein furious. He famously called the phenomenon spooky action at a distance. He spent the rest of his life refusing to accept it, because the alternative seemed monstrous, that one corner of the universe could affect another corner instantly, with no signal passing between them. Here is the strange part, the part that physicists circle around carefully. Entanglement does not let you send messages faster than light. Even though the correlation between the two electrons is instantaneous, you cannot use it to communicate. Why? Because the result of any single measurement is random. The New York physicist cannot choose whether her electron comes up, or spin down. She measures, and she gets one or the other, randomly. Her colleague on the moon also gets a random result, but always opposite to hers. Until the two compare notes, by ordinary slower-than-light communication, neither of them can tell that anything strange happened. They each see a random sequence of ups and downs. It is only when they line up their lists, side by side, that the perfect correlation appears. The universe, in some sense, has found a clever loophole. It allows two events at vast distances to be linked, but it forbids anyone from using the link to actually transmit information. The cosmic speed limit is preserved on the surface, even though something deeper underneath is happening that has no respect for distance at all. Physicists have lived uncomfortably with this for decades. The math is clear, the experiments are airtight, the interpretation, what is actually happening behind the math, remains contested. Some physicists say the two electrons are not really separate objects. Once entangled, they are a single thing, smeared across space. Distance does not apply to the link because the link is not crossing distance. It is part of a unified state that has no internal geography. Others say the universe really does have non-local connections that ignore the rules of space, but those connections cannot carry usable information, only correlations. Reality is non-local at the quantum level, but the non-locality is hidden from us in a way that prevents any practical violation of relativity. Still others appeal to multiple worlds, retrocausality, hidden dimensions, and frameworks where the very concept of a measurement is illusory. None of these has won the argument. All of them remain on the table. What is settled beyond any reasonable doubt is this: two electrons can be linked in a way that makes them behave as a single system across any distance. Measure one, and the state of the other becomes definite. Instantly. The link does not weaken with distance. It does not respect the geography of space. Einstein's last great hope was that this strangeness would dissolve once we found the right hidden mechanism. He believed there had to be a sensible local explanation, with little instructions tucked inside each particle that the math had simply missed. In the 1960s, an Irish physicist named John Bell figured out how to test that hope once and for all. He devised a mathematical inequality that any local hidden variable theory would have to obey. If experiments showed the inequality being violated, then no hidden instructions could explain the results. Either non-locality was real, or something even stranger was going on. Decades later, the experiments came back. The inequality was violated, decisively, repeatedly, by every group that ran the test. Einstein's hope was dead. John Bell's argument is one of the most beautiful in 20th century physics, and one of the most devastating. It is also surprisingly simple once you see the trick. Imagine two entangled electrons sent in opposite directions. At each end, a physicist can measure the spin along any of three different axes, chosen at the last moment, randomly. Call the axes A, B, and C. Each measurement returns either up or down. Bell asked what the correlations between the two ends should look like if there were no spooky action between the electrons. If each electron carried hidden instructions, some pre-programmed answer for what it should do under each possible measurement, then the correlations would have to obey a strict mathematical limit. He worked out what that limit was. It is called Bell's inequality. Now run the experiment using the actual rules of quantum mechanics. Calculate what the correlations between the two ends should be, with entanglement in full force. The numbers come out higher than Bell's inequality allows, significantly higher. Quantum mechanics predicts correlations that no hidden variable theory can produce. This means the question can be settled by experiment. You set up two entangled electrons. You run thousands of measurements with random access choices at each end. You compute the correlations. If they obey Bell's inequality, hidden variables are alive. Einstein wins. If they violate it, hidden variables are dead. Quantum non-locality is real. The first experiments were performed in the early 1970s and continued to grow more sophisticated through the 1980s and beyond. The results were consistent. Bell's inequality was being violated. Real entangled electrons produced correlations stronger than any local hidden plan could account for. But for years, skeptics could point to small loopholes. Maybe the detectors were not efficient enough. Maybe the random choices were not random enough. Maybe some signal was leaking between the labs. Each loophole had to be closed in turn, with cleaner experiments and cleverer setups. By 2015, the last major loopholes were closed. Multiple experiments around the world ran what physicists call loophole-free Bell tests, with detector efficiency, randomness, and isolation all rigorous enough to satisfy the strictest critics. The result was the same. Bell's inequality was violated. Local hidden variables were ruled out as a description of reality. In 2022, the Nobel Prize in Physics was awarded to John Clauser, Alain Aspect, and Anton Zeilinger for the experimental work that turned Bell's argument into a settled fact of nature. Einstein famously called entanglement spooky action at a distance, since the particles seemed to be communicating faster than the speed of light. Einstein, along with Boris Podolsky and Nathan Rosen, argued that hidden variables should be added to quantum mechanics to explain entanglement and to restore locality and causality to the behavior of the particles. Einstein had hoped that hidden variables would save the world he loved. The Nobel-winning experiments said no. Whatever quantum mechanics is doing, it cannot be explained by local instructions sitting inside particles before measurement. The implications are still being worked out, even now. One reading is that the universe really is non-local at its deepest level, that distant particles really do influence each other through some channel we cannot see, and that our familiar geometry of space is a kind of surface story over a deeper connected reality. Another reading is that the very idea of definite outcomes before measurement is wrong, that reality only crystallizes when an observation happens, and that the universe is fundamentally probabilistic in a way no classical picture can capture. Both readings are consistent with the data, both are unsettling. What is no longer in dispute is that an electron in your lab can share its fate with another electron across town, or across the planet, or across the galaxy, and that fate sharing is real. It does not depend on hidden notes passed between them. It is woven into how reality calculates itself. And if you find yourself wondering where, exactly, an electron is when no one is looking, the answer is the strangest of all. Forget the planetary picture. Forget the diagrams in old textbooks where the electron orbits the nucleus the way the Earth orbits the Sun, a tidy little ball tracing a tidy little circle. That image is wrong. It has been wrong for almost 100 years. Almost everyone still uses it, because the truth is harder to draw. When an electron is bound inside an atom, it does not have a position. It has a probability cloud, a fuzzy three-dimensional distribution that tells you the chance of finding the electron in any particular spot, if you happen to look. Until you look, the electron is not at any one place. It is spread across the cloud, with higher probability in some regions and lower in others, like fog of varying thickness around the nucleus. The cloud is real in every sense that matters. It interacts with other electrons. It defines the chemistry of the atom. It dictates how the atom binds to its neighbors. The cloud is what is doing the work, not some imaginary tiny ball at one point inside it. Different energy states correspond to different shapes of cloud. The lowest energy state in a hydrogen atom is a smooth spherical cloud thickest at the center, fading outward. Higher states have more complicated shapes. Clouds with 2 lobes, like a dumbbell. Clouds with 4 lobes, like a clover. Clouds with rings, with nodes, with empty surfaces running through them, where the probability of finding the electron is exactly 0. That last detail is worth stopping for. In some atomic states, the cloud has a surface inside it where the probability is 0. The electron can be found on either side of this surface, but never on it. It travels from one side to the other without ever passing through. It does not cross. It just appears, with vanishing odds of being caught in transit. If you tried to track the electron from one side of this nodal surface to the other, you would fail. There is no continuous path. The electron's existence on each side of the nodal surface is governed by the wave function's behavior, and the wave function is genuinely zero across that boundary. The electron is somehow on both sides without having moved between them in any classical sense. This is what an atom actually looks like. Not a miniature solar system, a nucleus surrounded by a stack of these strange sculpted probability clouds, each one defining where its electron is allowed to exist and where it is not. The clouds have names. Physicists call them orbitals, a holdover from the old planetary picture, even though no orbiting is happening. The first orbital is spherical. The next set has the dumbbell shapes, oriented along 3 different axes. After that come the clover shapes, then more elaborate forms with rings and lobes and nodal surfaces. Every one of them is a stationary pattern. The electron is not flying around inside the cloud. It is the cloud in some sense, a smeared-out probability that only sharpens into a single point when measured. Stack the orbitals up, fill them according to the exclusion principle, and you get the structure of every atom in the periodic table. The shape of the outermost cloud determines how the atom bonds with others. The geometry of those bonds determines the shape of every molecule. The shape of molecules determines the function of every protein in every living cell. Your life, your cells, your nerves, your thoughts, runs on the geometry of probability clouds, shaped by an electron that does not have a position. This is the part that sticks in the throat. We are made of objects whose location is undefined. Our chemistry is built on shapes that exist in possibility space, not in physical space. The reason your body works is that uncountable trillions of these clouds, in uncountable atoms, are all holding their precise probability geometries against the uncertainty principle, the exclusion principle, and the relentless quantum strangeness underneath. We treat the world as solid because the clouds are stable. We treat objects as in one place because the math averages out cleanly when the numbers are large enough. The illusion of a definite, localized world is real for us at our size, but at the scale of the things we are made from, location itself has dissolved into a mist of probability. And those probability clouds have shapes that look stranger than anything in classical geometry. In the next chapter you will see them, and they are beautiful. If you could somehow see the probability cloud of an electron, you would not see anything from your daily experience. You would see a gallery of shapes that look like sculpture from a civilization that did not evolve on Earth. The first orbital, the lowest energy state, is a sphere, smooth, fading from dense at the center to wispy at the edges, a foggy ball wrapped around the nucleus. Most chemistry textbooks show this, and it is the easiest to picture. The next set of orbitals are not spheres, they are dumbbells. 2 lobes joined at the nucleus, with a flat plane running through the middle where the electron is forbidden to be. There are 3 of these dumbbells in any atom, oriented along 3 perpendicular axes, 1 pointing up and down, 1 front and back, 1 left and right. The electron in any one of them is split between 2 regions of high probability, with empty space dividing them. Climb to the next energy level, and the clouds get stranger. Some of them look like 4-leaf clovers, with 4 bulbs of probability arranged around the nucleus, separated by surfaces of 0 probability. Others look like a dumbbell wrapped in a donut, a strange combination of lobe and ring. The shapes have names that portray how exotic they are: d orbitals, f orbitals, and as you climb higher in energy, they grow more elaborate, with more lobes, more nodes, more delicate geometric structure. These shapes are not artistic interpretations. They are the actual mathematical patterns of where an electron can be found, dictated entirely by the equations of quantum mechanics. Every atom in the periodic table is built by stacking electrons into these orbitals according to the exclusion principle, lowest energies first. The way the shapes overlap with neighboring atoms determines how molecules form, what angles their bonds take, and what shape the resulting structure has. Water is bent at a specific angle of about 104 degrees because of how the oxygen atom's orbitals are arranged. Methane is a tidy little tetrahedron because of the 4-way symmetry of carbon's outer orbitals. Benzene is a flat hexagonal ring because of how its electrons spread into a donut-shaped cloud above and below the carbon skeleton. Every chemical structure you have ever encountered, from table salt to your own DNA, takes its shape from the underlying geometry of these probability clouds. The strange thing is that the clouds are real, but the electron itself is not really inside them in any single spot. The cloud is the electron, in some sense. Until measured, the electron is the entire probability pattern, smeared across the orbital, simultaneously in every region the cloud allows, and in none of them in particular. You cannot point to an atom and say the electron is here. You can only say it is shaped like this dumbbell, this clover, this delicate three-dimensional pattern of denser and sparser regions. The shape exists, the location does not. Even more disquieting, electrons in atoms are constantly mixing between orbitals when energy is added or released. An electron in a low orbital, when given the right amount of energy, jumps into a higher one. The cloud changes shape almost instantaneously, the dense ball expanding into a dumbbell or the dumbbell contracting back into a ball. There is no intermediate stage. There is no gradual transformation. The electron does not slide from one shape to another. It is in one orbital, then it is in another. The transition is what physicists call a quantum jump. When the electron drops from a higher orbital back to a lower one, it releases the energy difference as a photon. That is where the colors of fire come from. That is where the light of a neon sign comes from. That is where every photon of starlight in the night sky comes from. Ultimately, electrons rearranging their probability shapes inside atoms, and the universe lighting up with the dropped energy. A geometry no one can directly see, made of probability instead of stuff, is what gives everything its color and chemistry. And tucked inside this picture is one of the most precise measurements ever made, the wobble that nearly broke modern physics, then unbroke it again. In the 1940s, physicists noticed that an electron, when placed in a magnetic field, wobbles. Specifically, it precesses, like a spinning top in gravity, tracing out a slow cone as it tips around the field's direction. The faster the wobble, the stronger the electron's magnetic response. The number that captures this, the so-called magnetic moment, is one of the most carefully measured quantities in all of science. Quantum theory, in its simplest form, predicted the wobble exactly. The number should be precisely 2 in the natural units physicists use. Beautiful, clean, done. Except experiments showed the number was not exactly 2. It was slightly more, by a small amount, about 1 part in 1,000. The wobble was a hair faster than the simple theory said it should be. This tiny excess is called the anomalous magnetic moment of the electron, and explaining it became one of the great challenges of 20th century physics. The deviation seemed small, but it was real, and any theory worth its salt had to account for it. The explanation, when it came, was beautiful and absurd in equal measure. The slight excess in the wobble was caused by the electron interacting with the seething sea of virtual particles that surrounds it at all times, the foam of temporary photons and electron-positron pairs that, according to quantum theory, are constantly popping in and out of existence in empty space. Each one of those interactions tugs on the electron just a little, nudging its wobble slightly faster. To calculate the anomaly precisely, physicists had to add up the contributions of all these virtual interactions, layer upon layer, with each layer harder to compute than the last. The first contribution gave a rough estimate. The second contribution refined it. The third refined it further. By the time the calculations had been pushed to extreme precision, the theoretical prediction matched the measured value to 14 decimal places. That is the most accurate match between theory and experiment in the history of science. Nothing in any other field comes close. The electron's wobble has become the gold standard against which the framework of quantum field theory is judged. Every time the calculation has been pushed further, the agreement has held. This success is why physicists trust quantum theory so deeply. The framework is bizarre, the philosophy is unresolved, the ontology is a mess. But when you compute, the numbers come out right. There is a less famous cousin of the electron called the muon, which is essentially a heavier electron. It also wobbles in a magnetic field, and its anomalous magnetic moment can be measured the same way. For decades, the muon's wobble showed a small but persistent disagreement with the predicted number, hinting that some unknown new physics, undetected forces, might be tugging at the muon in ways no one had accounted for. In 2001, the Brookhaven National Laboratory in Upton, New York, found that muons seemed to wobble slightly faster than the standard model predicts. 2 decades later, Fermilab's muon G2 experiment confirmed the anomaly, and the odds of it being a fluke were calculated at roughly 1 in 40,000. Physicists got excited. Maybe the discrepancy was the first crack in the framework, the first hint of physics beyond what we knew. New particles, hidden forces, exotic behavior just out of reach. Then, in early 2026, a team of theorists redid the calculation with a more powerful method. In a paper published in the journal Nature, a team led by a Penn State researcher described one of the most precise calculations ever performed in particle physics, showing that the standard model still holds. There were many calculations in the last 60 years or so, and as they got more and more precise, they all pointed toward a discrepancy and a new interaction that would upend known laws of physics. The team applied a new method to calculate this discrepancy quantity and showed that it's not there. Penn State University. The anomaly was not in nature, it was in the older calculations. The standard model survived again. The electron's wobble keeps physics honest. It is a number small enough to compute and exact enough to test. And every time we have measured it, the universe and the equations have agreed. For now, but the electron has not finished surprising us. In a thin sheet of carbon, electrons recently broke a rule of metals that had stood for a century and a half. Take a sheet of carbon exactly 1 atom thick. This is graphene, a single layer of carbon atoms arranged in a flat hexagonal lattice, like atomic chicken wire. It is one of the strangest materials humans have ever made. It is stronger than steel by weight, conducts electricity better than copper, and behaves in ways that have surprised physicists ever since it was first isolated in 2004. Now, take that sheet, cool it down to nearly absolute zero, and tune the energy of its electrons to a very specific point, the place where the material is balanced on the edge between conducting and not conducting. This is called the Dirac point. And at this point, something extraordinary happens. The electrons stop behaving like ordinary electrons. In a normal metal, electrons are independent. Each one carries its own charge and energy, bumping around through the metal's lattice, on its own. There is a famous law from the 1850s, the Wiedemann-Franz law, which says that in any normal metal, heat and electrical current must move in lockstep. The ratio between how well a metal conducts heat and how well it conducts electricity is fixed, set by fundamental constants of nature, and barely varies from one metal to another. It is one of the most reliable rules in the history of physics, holding for over a century and a half. In graphene at the Dirac point, the rule shatters. Researchers have found that electrons in graphene can break a long-standing rule of metal physics, separating heat flow from electrical flow by more than 200 times at low temperatures. The discovery shows that electrons in this atom-thin carbon material can move collectively as a quantum liquid rather than as independent particles. 200 times. The heat and the charge in graphene at the Dirac point come unhitched, and they begin to flow independently of each other in violation of a rule that has held for every other metal humanity has ever tested. The electrons stop being a collection of separate particles and become something else, a liquid, a coordinated fluid, a swarm acting as one. In that narrow window, electrons and holes behaved as one dense, self-organized mixture rather than as separate carriers. Physicists call this state a Dirac fluid, a liquid-like electronic phase that appears near graphene's balance point. A liquid made of electrons, not electrons sloshing through a liquid, electrons themselves behaving as a fluid, with collective motion, coordinated flow, and behaviors no individual electron could produce on its own. The strangest part is what this fluid resembles. Similar motion appears in quark-gluon plasma, an ultra-hot mix of subatomic particles linking this carbon sheet to far higher energies. Quark-gluon plasma is the state of matter that existed just after the Big Bang, when the universe was so hot and dense that ordinary particles could not form. Physicists recreate tiny droplets of it in particle accelerators by smashing heavy nuclei together at nearly the speed of light. The temperatures involved are unimaginable. The fluid that emerges briefly before it cools and falls apart has a specific kind of behavior, a low-friction, almost frictionless flow that is one of the most efficient liquid behaviors physics knows. The same kind of behavior shows up in graphene at the Dirac point, but at temperatures close to absolute zero, with energies 10 quadrillion times lower. The Dirac fluid is a cold temperature, low-energy mirror of the hottest, most extreme matter ever produced. Two completely different regimes of physics, the inferno of the early universe and a thin sheet of carbon in a chilled laboratory, are showing the same underlying mathematics. The fluid behavior of electrons in graphene gives physicists a tabletop window into states of matter that previously required particle accelerators to study. But the fluid does something even stranger than mimicking the early universe. In the right conditions, it does something no liquid is supposed to be able to do. The Wiedemann-Franz law is not just a rule, it is a description of what electrons do when they are minding their own business. Heat and charge flow together because each electron carries both a little energy and a little negative charge, moving through the metal as a single bundle. Push the electrons in one direction with a voltage, and you push their heat in the same direction, automatically. In the Dirac fluid in graphene, this stops being true in the most dramatic way imaginable. The heat and the charge do not just decouple, they move in opposite directions. By measuring both flows at once, Arindam Ghosh at the Indian Institute of Science showed that each moved the other way. Working with collaborators in Japan, Ghosh and colleagues found that the reversal sharpened exactly where collective motion should take over. Imagine a river that flows downhill, while the heat in the water flows uphill. Imagine a wire where the current goes one way and the warmth slides the other way. That is what the Dirac fluid does. The electrons coordinate themselves so that the negative charges drift one direction, while the heat they carry drifts the opposite direction, like two separate rivers occupying the same channel and refusing to mix. This is not subtle. The reversal is direct, measurable, and consistent. It is the strongest experimental sign yet that the electrons in graphene at this special point are no longer independent particles. They are organized. They are flowing as a coordinated state of matter with rules of motion that no classical electron can produce. Why does this happen? In an ordinary metal, the electrons are widely separated, sparse, and weakly interacting. Each one mostly ignores the others. They flow like grains of sand poured down a chute, independent, uncoordinated, plenty of room between them. In graphene tuned to the Dirac point, the situation flips. The electrons are dense relative to the available states. The temperature is low, and the interactions between them become strong. The electrons stop ignoring each other. They begin to feel one another's presence. They start to move collectively, the way water molecules move together, rather than as a bunch of unrelated billiard balls. Once they move collectively, the rules change. The fluid has its own dynamics, its own way of carrying heat and charge. It is no longer governed by the simple single-particle physics that gave us the Wiedemann-Franz law. It is governed by the equations of fluid flow, applied to a fluid made of pure quantum particles. The discovery has been building for years. Earlier experiments hinted at fluid-like behavior in graphene, but could not quite nail down the key signatures. Earlier experiments had seen pieces of the puzzle, yet the key electrical value of the flow stayed unsettled. The new devices pushed it toward the quantum of conductance. That constant is a basic step size for electrical flow, and landing near it made the new result much harder to dismiss. When the electrical conductivity in the fluid landed close to the quantum of conductance, a fundamental constant, the result became impossible to ignore. The fluid was not an artifact of dirty samples or measurement quirks. It was a genuine state of matter with its own deep properties hidden inside an ordinary-looking sheet of carbon. What this means for science is hard to overstate. The Dirac fluid gives physicists a tabletop laboratory for studying behaviors that previously required either the conditions of the early universe or the inside of neutron stars. It opens up new ways to think about superconductivity, exotic phases of matter, and the strange in-between states where quantum mechanics and fluid dynamics collide. The electron, alone, is already weird. The electron, in a coordinated swarm, becomes something altogether different. And in early 2026, another graphene experiment showed an electron fluid doing something even more impossible, freezing solid in a way that should not be allowed. Some things in nature are supposed to keep moving. A superfluid is one of them. A superfluid is an exotic state of matter where particles flow without any resistance at all. No friction, no drag, no slowing down. They will climb walls. They will leak through pores so tight that ordinary liquids cannot pass. They are, in their pure form, defined by the fact that they cannot stop. In early 2026, in an ultra-cold graphene experiment, physicists watched one stop. Physicists have watched a quantum fluid do something once thought almost impossible: stop moving. In experiments with ultra-thin graphene, researchers observed a superfluid, normally defined by its frictionless flow, freeze. A superfluid that freezes is a contradiction in terms. It is the equivalent of fire becoming ice. Whatever made the fluid frictionless should have prevented it from ever becoming a solid. And yet, in the right conditions, the electrons in this carbon sheet did exactly that. They were flowing without resistance, then they were not flowing at all. The result was so unexpected that the lab spent months running checks before publishing. Each test confirmed the same thing. The superfluid had genuinely come to a stop. The electrons, locked together in a coordinated quantum state, transitioned into some kind of frozen pattern, a still arrangement that broke every rule of how a superfluid is supposed to behave. What is going on? The current best theory is that the electrons in the superfluid, at this critical condition, condense into a different kind of pattern, something more rigid, more locked in, more solid-like. The collective state stops being a flow and becomes a fixed structure, with the electrons holding their relative positions in some quantum-correlated way. The fluid does not become a normal solid. It becomes a quantum solid, a frozen pattern of probability, instead of a frozen pattern of stuff. Even more strangely, the freeze appears to be reversible. Tune the conditions back, and the frozen pattern melts again into a flowing superfluid. The electrons have multiple coordinated states available to them, and they slide between these states as the experimental knobs are turned. Like ice melting and refreezing in a strange thermodynamic dance no other material has ever performed. The implications are still being worked out. The frozen superfluid joins a small list of newly discovered electron states that defy every textbook expectation. The Dirac fluid, the frozen superfluid, the heat charge reversal, all of these are things electrons in graphene are doing that electrons in any other system have never been seen to do. There is a pattern. The electron, when given the right environment and the right conditions, becomes something new. Not a particle. Not even a wave. A coordinated collective entity with rules of behavior that look almost more like a phase of reality than a phase of matter. Physicists are starting to suspect that graphene is not unique. It is just an unusually clean and accessible window into behaviors that the electron has been capable of all along, waiting for the right conditions to reveal them. There may be many more electron states out there hidden in materials we have not yet built, with rules of motion no one has ever imagined. For now, the frozen superfluid sits as a fresh discovery, barely months old, and the field is buzzing about what it means. Each new state of electrons in graphene rewrites a small part of what physics thought it knew. Each one shows the electron, that one tired century-old particle, capable of doing something we never imagined. And in a stunning twist, some of these graphene effects show patterns that connect cold electrons in carbon sheets to the most extreme matter the universe has ever produced. Quark-gluon plasma is the most extreme state of matter known. It existed for roughly a millionth of a second after the Big Bang, when the universe was so hot and so dense that ordinary protons and neutrons could not yet form. Quarks and gluons, the particles that normally are bound tightly inside nuclei, were free, swimming together in a fluid of impossible energy. Physicists recreate tiny droplets of this plasma at facilities like the Relativistic Heavy Ion Collider in New York. They smash gold nuclei together at almost the speed of light, generating temperatures of trillions of degrees in microscopic volumes. For unimaginably brief moments, the plasma forms, exists for a billionth of a trillionth of a second, then cools and falls apart into ordinary particles. During its brief life, scientists measure how it flows, how it conducts heat, how its energy redistributes itself. What they have learned is that quark-gluon plasma flows like a nearly perfect fluid. Its viscosity is among the lowest ever measured. It is, by some measures, the most ideal liquid in the known universe, a liquid with almost no internal friction at all. Now compare this to the Dirac fluid in graphene at the Dirac point. Kept at near absolute zero, The Dirac fluid also flows with very low friction. It also redistributes heat and charge in coordinated, almost ideal ways. The mathematics describing its behavior shares deep structural similarities with the equations for quark-gluon plasma, even though the two systems exist at energies and temperatures that differ by a factor of about 10 quadrillion. This is one of the great surprises of modern physics. The hottest substance ever produced and the coldest sheet of carbon imaginable are, in a sense, doing the same thing. Why? Because the underlying mathematics, the equations of strongly interacting quantum fluids, depends not on the absolute scale of energy, but on the relative strengths of the interactions and the symmetries of the system. When the conditions are right, two systems that look completely different on the outside can flow according to the same rules on the inside. This is sometimes called duality. A small, accessible, low-energy system can mirror the behavior of an enormous, inaccessible, high-energy system. By studying the small one, physicists gain insight into the large one. By understanding electrons in a thin carbon sheet, they sharpen their understanding of the matter that filled the early universe. The implications are wider than they first appear. Strongly interacting quantum fluids show up in many places: inside neutron stars, in the cores of certain dying stars, in some exotic states of nuclear matter that are otherwise impossible to reach. If graphene's Dirac fluid mirrors the behavior of these systems, then graphene becomes a tabletop simulator for environments that physicists otherwise can only theorize about. There is something humbling and exhilarating about this. The electron, that ordinary ubiquitous particle, when put into the right kind of crystal, becomes a working model of the early universe. Cool it, tune it, watch it flow. The same equations that describe the hottest soup in cosmic history are playing out in your benchtop sample, and the electron is the actor performing the lead role. This connection points to something deeper about what an electron actually is. It is not just a particle. It is a node in a vast network of mathematical possibilities, a flexible character that can play many roles depending on its environment. In a metal, it is a charge carrier. In an atom, it is a probability cloud. In an entangled pair, it is part of a non-local link. In graphene, at the Dirac point, it is a participant in a quantum fluid that mirrors the early universe. The same particle, different stages, completely different scripts. The flexibility of the electron, its ability to wear so many costumes, follow so many rules depending on context, is part of what makes it so hard to pin down. It is not just one thing being itself, it is one thing capable of being many things, and physics is only beginning to map the full catalogue. And in the next chapter, you meet the strangest costume of all, the electron's evil twin. In 1928, the British physicist Paul Dirac was trying to write down an equation that would describe the electron in a way that respected both quantum mechanics and Einstein's relativity at the same time. He succeeded. The equation he found, which still bears his name, is one of the most beautiful in physics. But the equation had a strange feature. When he solved it, he got two sets of answers. One set described the electron exactly as expected. The other set described something that should not exist. The second set described a particle with the same mass as the electron, but with the opposite electric charge. A positively charged electron, a mirror image, a twin made of opposite stuff. Dirac was not sure what to do with the second solution. He tried to interpret it as protons, hoping that the equation was somehow describing the proton as the electron's positive partner, but the math would not allow it. The mirror twin had to have exactly the same mass as the electron, and protons are nearly 2,000 times heavier. The two could not be the same kind of object, so Dirac, with great reluctance, predicted the existence of an entirely new particle, a particle with the electron's mass and the opposite charge. He called it the anti-electron. Today we call it the positron. He published his prediction in 1931. Most physicists thought it was a mathematical artifact, the equation playing tricks. The idea that nature contained an anti-version of the most common particle in the universe seemed like science fiction. 2 years later, in 1933, an American physicist named Carl Anderson found one. He was studying cosmic rays, high-energy particles arriving from space, and saw a track in his cloud chamber that curved the wrong way. It had the mass of an electron. It had the opposite charge. It was the positron, exactly as Dirac had predicted. This was one of the most profound moments in 20th century physics. A particle had been predicted purely on the basis of mathematical elegance, and then found in the real world. The math was not just describing nature, the math was telling us what nature contained before we had any direct evidence for it. The discovery opened the door to an entire mirror universe. For every particle in the Standard Model, there is an antiparticle, a partner with the same mass and the opposite charge. Antiprotons, antineutrons, antiquarks. Together these form antimatter, the strange and beautiful counterpart of ordinary matter. When matter and antimatter meet, they annihilate. An electron and a positron, brought together, vanish in a flash of pure light, their entire combined mass converted into photons by the equation everyone knows. Energy equals mass times the speed of light, squared. There is no residue, no debris. Two particles of stuff become two particles of pure radiation. In the cleanest, most violent reaction in physics. Hospitals use this every day. Positron emission tomography scans, the PET scans you may have heard of, work by injecting a slightly radioactive substance into the body that emits positrons. Each positron, the moment it is created, finds a nearby electron and annihilates with it, producing two photons that fly off in opposite directions. By detecting those photons, the machine maps where the radioactive substance is, and therefore what is happening inside the patient's body. Antimatter, once a wild prediction, is now a routine medical tool. The strangest part of the story is that antimatter is rare. The universe, by all observation, is overwhelmingly made of matter. There is far more electron than positron, far more proton than antiproton, far more atom than anti-atom. Why is this? Nobody knows. The early universe should have produced equal amounts of both, and they should have all annihilated each other, leaving behind a cosmos of pure light. Instead, a tiny imbalance, about one extra particle of matter for every billion pairs of matter and antimatter, survived the great early annihilation, and that small surplus is what built every star, every galaxy, every atom of you and me. The reason for the imbalance is one of the deepest open questions in physics. But the existence of the anti-electron itself is no longer in doubt. The mirror twin is real. There is a way to make an electron out of nothing. You will need a powerful gamma-ray photon, a nearby nucleus to soak up the recoil, and a sufficiently energetic environment. Get the conditions right and the photon disappears. In its place, two new particles appear, an electron and a positron, flying off in opposite directions. This is called pair production, and it is one of the strangest tricks the universe knows. Read the trade carefully. A particle of pure light, with no mass, no charge, and no other features beyond its energy, vanishes. In its place, two particles with mass appear, each with electric charge, each with a position and momentum, each one a fully formed quantum object. The energy of the photon has been converted into the matter of the two new particles, with the leftover going into their kinetic energy. The reason two particles always appear, rather than just one, is conservation of charge. The photon carries no electric charge. Whatever it produces must carry no net charge either. So, if it produces an electron with its negative charge, it must also produce a positron with its positive charge to balance the bookkeeping. This is happening right now in places around the universe where high-energy radiation is interacting with matter, near black holes, inside the cores of dying stars, in the violent jets of distant active galaxies. Wherever there is enough energy concentrated in a small enough region, photons are constantly transforming into pairs of new particles, populating the universe with fresh electrons and positrons that did not exist a moment before. The reverse process happens just as readily. An electron and a positron, brought close together, annihilate into photons. Matter to light, light to matter, in a constant exchange that the universe maintains as casually as you breathe. Pair production is one of the strongest pieces of evidence that an electron is not a fundamental, indestructible thing. It is something that can be made and unmade, something that emerges from energy when the conditions allow it, and dissolves back into energy when its twin meets it. The electron is more like a wave that the universe is allowed to set up, given enough energy, than like a marble that has always existed. This raises a strange question. If electrons can be created from energy, Where do the electrons in your body come from? Trace any electron in your body backward in time. Was it always an electron? Or was it once a photon that decayed into a particle pair, one of which eventually wound up in you? The answer, as far as physics can tell, is that most of the electrons in ordinary matter were created during the early universe, in the seething hot soup of the first second after the Big Bang. Pair production was happening on an unimaginable scale, with photons constantly transforming into matter and antimatter pairs, and matter and antimatter pairs constantly annihilating back into photons. A near-perfect balance was maintained. Then, for reasons no one fully understands, the balance broke. A slight excess of matter over antimatter survived the great mutual annihilation. The leftover matter, the tiny surplus that did not find a partner to annihilate with, became the universe of stars and planets and people that we now inhabit. Every electron in your body is, in some sense, a survivor, a particle of an unknown asymmetry, a leftover from a bookkeeping error in the first moments of the cosmos. Without that error, there would be no electrons at all, only an empty universe full of light. Pair production also tells us something important about the nature of the vacuum. The vacuum is not empty in the sense your everyday intuition suggests. It is a place where particles can be created from energy, where antimatter and matter can briefly form, and where the rules of who exists and who does not are constantly being negotiated. The vacuum is a stage. The electron is one of its leading actors. Before he could believe in positrons, Paul Dirac proposed an even stranger idea. To make sense of the negative energy solutions in his equation, the solutions that turned out to describe antimatter, he suggested that what we call empty space might not be empty at all. Dirac proposed that the vacuum is filled, completely filled, with an infinite sea of electrons sitting in negative energy states. An ocean of unseen electrons stacked invisibly behind reality, packed into every possible negative energy slot. We do not see this sea because it is uniform. It surrounds us, permeates us, and offers no contrast. Like a fish that does not notice the water, we do not notice the sea because there is nothing to compare it to. A positron, in this picture, is a hole in the sea, a missing electron. When energy comes in and lifts an electron out of the negative energy sea into ordinary positive energy space, it leaves behind a vacancy. The vacancy behaves like a particle with positive charge because the electron that was supposed to be there is missing, and the same mass as an electron. The lifted electron is the new electron we see. The vacancy is the positron. This idea was, frankly, an infinite sea of electrons hidden behind every cubic inch of space. With antimatter being holes in that sea, it sounded like a fairy tale told to a child to make the math behave. But here is the strange thing. It worked. The Dirac sea picture made correct predictions about how electrons and positrons would behave. It explained pair production naturally. Energy creates a hole in the sea by lifting an electron out, and we see the hole and the lifted electron has two new particles. It explained annihilation just as cleanly. An electron drops back into a hole in the sea, and the energy is released as photons. Pair production and annihilation are simply electrons jumping in and out of the negative energy sea, with the splashes appearing to us as particles being born or destroyed. Modern quantum field theory has largely replaced this picture with a more abstract framework. Today, physicists describe particles and antiparticles as excitations of underlying fields, without needing the metaphor of a sea of electrons. The math is cleaner, the picture is less colourful, but the Dirac sea was not wrong. It was an early imaginative attempt to grasp something deep about the structure of reality, and it captured something true. The vacuum is not empty, it has structure, it has content. It can give birth to particles and absorb them again. Whether you describe that content as a sea of electrons, or as a foam of fields, or as some other framework yet to be developed, the underlying truth is the same. There is no such thing as nothing. What is striking is how often Dirac's mathematical leaps turned out to describe nature. The relativistic equation, which produced antimatter as a side effect, the negative energy sea, which gave us a working picture of pair production, the positron, predicted before it was found. Each step felt, at the time, like reckless mathematical fantasy. Each step turned out to be physics. There is a lesson in this about the nature of physical theories. Sometimes the math knows things the physicists do not. Sometimes the equations contain solutions that look absurd, that seem like errors, that clearly describe something that cannot exist. And sometimes those absurd solutions describe parts of nature that we have not yet noticed, and they are quietly waiting for us to catch up. The electron story is full of moments like this: predictions that seemed crazy, solutions that looked wrong, equations that pointed at things no one believed could be real. Every time, eventually, nature turned out to agree with the math, and our picture of the universe expanded. The Dirac sea is a reminder that the vacuum has secrets, and the electron is one of the most important characters in the story of those secrets. The Standard Model of particle physics is the most successful theory of matter ever built. It contains a precise list of every elementary particle currently known, organized by their properties, spin, charge, mass, behavior under various forces. It is a periodic table for particles, and it has predicted the existence of new particles before they were found, including the famous Higgs boson, discovered in 2012. The electron sits in this table in a simple, unmistakable place. It is one of three particles called charged leptons. Its two heavier cousins are the muon, mentioned earlier in connection with its anomalous magnetic moment, and the tau, a much heavier and more unstable particle. All three carry the same negative charge as the electron. All three have the same kind of spin. They differ only in mass. Why are there three? Nobody knows. The Standard Model contains the existence of the muon and the tau as a brute fact. They are heavier, less stable copies of the electron, and they exist for no reason the model can explain. The muon is about 200 times heavier than the electron. The tau is about 3,500 times heavier. The pattern is not a smooth multiplication, not a recognizable mathematical sequence. It is just three numbers, sitting on the page, with no underlying logic that anyone has been able to find. This is one of the deep mysteries the Standard Model does not solve. Why three generations of charged leptons? Why are their masses what they are? Why do the heavier two exist at all, given that ordinary matter is built almost entirely from the electron? The mystery deepens. The model also contains three generations of neutrinos, the ghostly neutral particles produced in radioactive decay and nuclear reactions. There are three generations of quarks, the constituents of protons and neutrons. The three-generation pattern repeats throughout the model, in every category of fundamental particle. Three sets of nearly identical copies, with masses that climb by huge factors, but follow no clean rule. If you ran the universe again with slightly different masses, almost everything we know would change. Electrons too heavy and atoms collapse, electrons too light, and stable matter becomes impossible. The universe seems balanced on a knife edge, with the electron's specific mass, 511,000 electron volts in physicist units, fine-tuned to allow stars, chemistry, and life to exist. The Standard Model takes this fine-tuning as input. It does not explain it. It does not predict it. The mass of the electron, like the masses of all other fundamental particles, is a number you put into the model by hand, copied from experiment. What the model does explain beautifully is how the electron interacts with other particles. The math of these interactions is called quantum electrodynamics, or QED, and it is the most precise theory in the history of science. We have already mentioned that the electron's anomalous magnetic moment is calculated to 14 decimal places by QED, and matches experiment perfectly. That accuracy extends to almost every prediction QED makes about how electrons behave around photons and other charged particles. But the success of QED is built on a foundation that we have already seen is shaky. The infinities, the renormalization, the bare masses subtracted from infinite clouds. All of these are technical workarounds that produce correct numbers without telling us why the universe is the way it is. The electron's mass goes in by hand. The charge goes in by hand. The structure of the equations is chosen to match what we observe, not derived from some deeper principle. So the Standard Model is, in a sense, a magnificent description of what electrons do, and a complete failure to explain why electrons exist or have the properties they have. It is the best we have. It is also clearly incomplete. Many physicists believe there is a deeper theory waiting to be discovered, one that would explain the masses of the leptons, the existence of three generations, and the underlying structure that produces the Standard Model, as a kind of low-energy approximation. String theory, supersymmetry, and various other proposals all try to fill this gap. None has yet succeeded. The electron is, in one sense, well understood. We can predict its behavior to extreme precision. In another sense, it remains a mystery, a particle whose properties we have measured, but whose deeper origin is still unknown. Quantum electrodynamics, or QED, is the theory of how electrons and photons interact. It was developed in the late 1940s by Richard Feynman, Julian Schwinger, and Shinichiro Tomonaga, who together earned the 1965 Nobel Prize for their work. It is the theory that finally tamed the infinities that had plagued earlier attempts to combine quantum mechanics with electromagnetism. The achievement is staggering. QED describes every interaction between electrons and photons, every emission of light, every absorption, every scattering, every magnetic interaction, using a small finite set of rules and equations. Apply the rules, run the calculations, and you get predictions that match experiment to a precision unmatched anywhere else in science. The standard example is the electron's anomalous magnetic moment. The QED prediction agrees with measurement to 14 decimal places. To put that in perspective, it is like measuring the distance from New York to Los Angeles and getting an answer that agrees with reality to the width of a single atom. No other theory in physics, in any field, achieves this kind of precision. The trick that makes QED work is a graphical method invented by Feynman, now called Feynman diagrams. To compute the probability of any electron-photon interaction, you draw all the possible ways the interaction could happen, all the paths an electron and a photon could take, all the intermediate particles they could exchange, all the loops and detours they might make. You assign each diagram a number based on simple rules. You add up all the numbers. The total tells you the probability of the outcome. The catch is that there are infinitely many possible diagrams. To get more accurate answers, you have to include more of them. The simplest diagrams give a rough estimate. Adding the next set with one extra interaction refines the estimate. Adding the set with 2 extra interactions refines it further. Each additional level of complexity is harder to compute, but each one brings the prediction closer to the measured value. The diagrams reveal something deep about the electron. Each diagram shows the electron interacting with virtual photons, temporary particles that flicker into existence, mediate a force, and vanish again. The electron is never alone. It is always exchanging photons with itself, with the surrounding electromagnetic field, with whatever charged particles are nearby. Every interaction it has is a bubbling cloud of virtual photons being emitted and reabsorbed in patterns dictated by the rules of QED. This is what gives the electron its anomalous magnetic moment. The simple version of theory without virtual particles predicts that the electron's wobble in a magnetic field corresponds to a magnetic moment of exactly 2. The actual measured value is slightly higher because the electron is constantly emitting and absorbing virtual photons, and each one nudges the wobble by a tiny amount. Add up all the nudges, and you get the small correction that takes the magnetic moment from 2 to its measured value. QED's success is so total that it has become the model for how physicists try to build theories of everything else. The strong force which holds nuclei together was tamed by a similar approach called quantum chromodynamics, or QCD. The weak force, which causes radioactive decay, was unified with electromagnetism in the electroweak theory. Each new framework extends the QED approach to a new corner of nature. But QED's success, as we have seen, depends on the trick of renormalization, the controlled cancellation of infinities, and on inputting the electron's mass and charge by hand, rather than deriving them from deeper principles. QED tells us how the electron interacts. It does not tell us what the electron is. This is the strange duality at the heart of modern physics. We have a theory that predicts the behavior of one particle to 14 decimal places, and we still cannot answer the simplest questions about it. What is its size? Why does it have the mass it has? Why does it exist at all? The most accurate theory in human history is, in another sense, a theory that has nothing at all to say about why the world is the way it is. It is a description of how, never of why. When QED says the electron is constantly surrounded by virtual photons, it is not speaking metaphorically. According to quantum field theory, every electron in the universe is at every moment exchanging a steady stream of virtual particles with the surrounding electromagnetic field. The electron emits a photon, then reabsorbs it. It splits into a virtual electron-positron pair, which then merges back into a single electron. It exchanges photons with nearby charged particles. All of this happens at scales smaller than an atom, and at speeds we cannot directly observe. The companions are called virtual because they cannot be detected on their own. They exist only in the act of an interaction. They are temporary, ephemeral, popping in and out of existence on borrowed energy that the universe permits because of the time-energy uncertainty principle. A virtual particle can exist for a brief moment as long as no one has time to measure it carefully. But the effects of these virtual particles are absolutely measurable. They cause the electron's magnetic moment anomaly. They produce a tiny shift in the energy levels of hydrogen, the famous Lamb shift, measured in 1947, which started physicists down the path of QED. They alter the way two electrons scatter off each other. They are the reason every prediction of QED includes corrections that go beyond simple naive calculations. The deeper picture that emerges is unsettling. The vacuum, what we ordinarily call empty space, is not empty. It is a seething, restless medium full of virtual particles flickering in and out of existence on every conceivable scale, in every conceivable variety. Photons appear and disappear. Electron-positron pairs form and annihilate. Even more exotic particles, briefly borrowed from the universe's energy budget, dance through the vacuum in patterns we are only beginning to understand. When an electron sits in this vacuum, it is not a lonely particle in empty space. It is a particle surrounded by a buzzing cloud of these virtual visitors, all interacting with it, all altering its properties slightly, all contributing to the dressed appearance we measure with our instruments. The bare electron, the electron without its cloud, is something we can never directly see. What we see is always the dressed version, the electron plus the swarm of virtual particles it carries with it everywhere. This is the deep reason for the renormalization trick. The infinities in our equations come from trying to describe the bare electron alone as if it were a lonely point in empty space. The cloud of virtual particles is part of what makes the electron's measured properties finite, and renormalization is the formal process of acknowledging that we can never separate the electron from its cloud. We measure the package, we compute the package. The infinities cancel because they were artifacts of asking about something, the bare particle, that nature never shows us. The vacuum's restlessness has deeper consequences that go far beyond the electron. The same virtual particle dynamics that surround every electron also fill the universe between electrons. Empty space carries energy, the so-called vacuum energy, which appears in cosmology as a contribution to the acceleration of the universe's expansion. Many physicists believe this vacuum energy is related to the dark energy that is currently driving distant galaxies apart at increasing speeds. The connection is not yet pinned down, but the underlying idea is clear. The vacuum is doing things, and what it does affects the universe at every scale. For the electron, the cloud of virtual particles is constant company. Every electron in your body, in this room, in the sun, in every star, is surrounded by its private cloud of flickering invisible companions, contributing their tiny corrections to its mass, its charge, its magnetic behavior. The electron is alone for not a single instant of its existence. In some sense, it is fairer to say that the electron is not just a particle. It is a particle plus its environment, an inseparable bundle of point and cloud, observable only as a unit, computable only with the cloud included. The thing we call the electron is the package, not the bare core inside, and the vacuum that surrounds it is not empty. It is the most active, restless, bustling medium in the universe. For most of human history, vacuum meant nothing, empty space, the absence of anything. Aristotle famously argued that nature abhors a vacuum, that empty space could not exist, that something must always fill the void. Modern physics has shown that he was, in a strange way, right, though not for the reasons he imagined. The vacuum, as quantum field theory describes it, is the lowest energy state of the universe. It is empty in the sense that nothing real, nothing measurable as a particle, is there in any persistent way. But it is not nothing. It is a state of fields, the underlying mathematical objects that fill all of space, that are fluctuating constantly, producing transient particle pairs and ephemeral disturbances on every scale. How active is the vacuum? The answer, as far as physics can tell, is incredibly active. At every cubic centimeter of space, virtual particles are being created and destroyed at rates and energies that, if added up naively, would give the vacuum an energy density so enormous it would have ripped the universe apart in the first instant of the Big Bang. The expected energy and the observed energy of the vacuum disagree by something like 120 orders of magnitude, the worst prediction in the history of physics. This is called the cosmological constant problem, and it is unsolved. What this means is that the vacuum is doing something we do not understand. Our equations say it should be vastly more energetic than it appears to be. Reality says it is calm enough to permit a stable universe. Some unknown mechanism must be cancelling almost all of the predicted energy, leaving behind only a tiny residue, but enough to drive the observed acceleration of cosmic expansion. We see the residue. We do not see why the cancellation is so nearly perfect. For the electron, the vacuum is not just a backdrop. It is a participant in everything the electron does. Every measurement of the electron's properties is also indirectly a measurement of how it interacts with the vacuum. The Lamb shift, the anomalous magnetic moment, the small energy corrections in atomic spectra, these are all signatures of the vacuum reaching out and tugging at the electron in patterns we can compute. Place two uncharged metal plates very close together in a vacuum, and they will be pushed together by a small but real force. This is called the Casimir effect, predicted in 1948 and measured directly half a century later. The force comes from the vacuum's fluctuations being slightly different between the plates than outside them, producing a tiny pressure that pushes the plates inward. The vacuum is not pushing in the colloquial sense, but its energy has structure, and that structure produces measurable forces on objects. Even more strangely, the vacuum can be deformed. In strong gravitational fields, near the edges of black holes, the vacuum structure is altered enough to produce real radiation. This is Hawking radiation, predicted by Stephen Hawking in 1974. The basic idea is that virtual particle pairs forming near a black hole's horizon can be torn apart, with one falling in and the other escaping as a real particle. The black hole loses energy. The vacuum around it has effectively been mined. Black holes evaporate slowly because the vacuum near their edge is not the same as the vacuum far away. The electron lives in this vacuum. Every electron everywhere is constantly interacting with these fluctuations, these subtle structures, these unmeasurable but real features of so-called empty space. What the electron is, at the deepest level, is inseparable from what the vacuum is. This is part of why physics has such trouble pinning down the electron's nature. The electron is not standing alone in empty space, where its properties could be described in isolation. It is enmeshed in the vacuum. And the vacuum is the most complicated, least understood object in physics. To understand one is to need to understand the other. We are made of particles that live inside a medium we cannot fully describe. The miracle is that we can predict their behavior at all, given how strange the medium is. The mystery is what happens when we can finally describe both. For nearly a century, the electron has been treated as fundamental. No structure, no constituents, no internal workings. It is what physicists call a true elementary particle, a building block that cannot be broken down further into smaller pieces. This may not be the final word. A small but persistent group of researchers have spent decades looking for any hint that the electron is not truly fundamental, that there might be something inside it, some smaller structure or pattern that explains its mass, its charge, its strange properties. The motivations are several. The standard model leaves the electron's mass unexplained. The infinities in the equations hint that something deeper is being missed. The fact that there are 3 generations of leptons, with no obvious reason, suggests that maybe the electron, the muon, and the tau are not 3 separate particles, but 3 different states of some underlying object. The experimental evidence so far is consistent with the electron being structureless. Every scattering experiment ever done, every test of how the electron interacts with high-energy probes, has shown no sign of internal structure, down to the smallest scales we can resolve. The current upper limit on the electron's size is about 10 to the minus 22 meters, far smaller than any structure ever directly observed. If the electron has parts, they are smaller than this. But absence of evidence is not evidence of absence, and there are theoretical reasons to suspect the electron may eventually reveal a deeper layer. Some grand unified theories predict that, at extremely high energies far beyond anything we can produce in laboratories, the electron might dissolve into more fundamental constituents, preons, as they are sometimes called. String theory takes a different approach, suggesting that all elementary particles are not points or balls, but tiny vibrating strings, with different vibrational patterns producing different particles. The electron, in string theory, is one specific note in a cosmic instrument, and the structure is the geometry of the vibration itself. Recent theoretical work has even questioned the standard interpretation of the electron's point-like nature. In a recent article on the size of the electron, the formulas of quantum field theory and the corresponding cross-sections are shown to be consistent with an extent of the electron of the size of the classical electron radius. The assumption that the relativistic energy of electrons in the high-energy limit consists solely of deformation energy from the extended electron density distribution allows for a simple interpretation of the experimental cross-sections. The author argues that distinguished physicists have avoided elaborating on the possibility of a finite electron extent, even though the evidence does not strictly require point-like behavior. The disagreement is not yet settled. Most physicists still treat the electron as point-like, both because it is consistent with all current data and because the math is simpler that way. A minority think we may be missing something important by doing so. If the electron does turn out to have internal structure, the implications would reshape physics. The standard model, with its 3 generations of leptons and quarks, might be revealed as a low-energy approximation of a deeper theory in which all of these particles are different configurations of the same underlying objects. The infinities that have plagued physics for nearly a century might finally have a natural resolution, with the electron's true structure providing the cutoff that current theories impose by hand. The reason the electron has the mass it does, the charge it does, the spin it does, might finally become explainable rather than inputs we set by experiment. For now, this is speculation. The experimental results are clean, the electron behaves as a point, but there is a small persistent feeling in the physics community that we may not yet have asked the right questions. Pushed to higher energies far beyond what any current accelerator can produce, the electron might one day reveal itself to be something other than a point, a small vibrating string, a composite of more fundamental things, a pattern in some deeper mathematical structure that we are only beginning to glimpse. The honest answer to what an electron is, at the deepest level, is that nobody knows. The most fundamental particle in the building blocks of you and me may turn out to be not so fundamental after all. There is one question woven through everything we have seen that physics has never managed to answer. When an electron is in a superposition, in a probability cloud, undefined, spread across multiple possibilities, and then a measurement happens, what is the measurement actually doing? What turns the cloud into a single result? What collapses possibility into actuality? This is called the measurement problem, and it is the deepest unresolved question in quantum mechanics. The bare facts are clear. Before measurement, the electron's wave function is a smooth, continuous, mathematical object that evolves according to the Schrödinger equation. After measurement, the wave function is no longer the smooth thing it was. It has snapped into a single result, with all other possibilities gone. The smooth evolution does not predict this snap. The snap happens somehow at the moment of measurement, but the equations of quantum mechanics do not contain any rule for when or why it occurs. Generations of physicists have proposed explanations. Each one has problems. The Copenhagen interpretation, the oldest and most common, says that the wave function is not a real physical thing but only a tool for predicting measurement outcomes. When a measurement happens, the wave function collapses. End of story. This works in practice but has the awkward feature of dividing the world into quantum systems and classical observers, with no clear rule for where the line is. What counts as an observer? A scientist? A camera? A single atom? The interpretation does not say. The many worlds interpretation, proposed by Hugh Everett in 1957, takes a more radical approach. There is no collapse. The wave function never snaps. Instead, the universe itself splits at every measurement, with each possible outcome occurring in a separate branch. When you measure the electron's spin and find it up There is another version of you in another branch of reality who measured down. The full wave function includes all branches. We see only one because we are part of one. This interpretation removes the measurement problem at the cost of admitting that there are uncountably many parallel realities, none of which we can observe. Pilot wave theories, originally proposed by Louis de Broglie and developed by David Bohm, suggest that particles always have definite positions, but their motion is guided by a hidden wave that obeys quantum equations. The randomness of measurement comes from our ignorance of the particle's exact starting conditions. The wave is real, the particle is real, and there is no collapse. Only the wave guiding the particle along a path that depends on the entire experimental setup. This interpretation is non-local in a deep way, and most physicists find it unsatisfying for technical reasons, but it remains a serious option. Other interpretations include consistent histories, relational quantum mechanics, objective collapse models, and various retrocausal proposals where the future influences the past. Each has its supporters, none has won decisively. What is striking is that all of these interpretations agree on the predictions. They all give the same numerical answers for every experiment. The disagreements are about what is really happening behind the math, and physics does not yet have a way to test which picture is correct. The mathematics describes the behavior with perfect accuracy. The story behind the math is open. For the electron, this means that the fundamental nature of its existence, whether it is in a single state, all states at once, or branching across multiple universes, depends on which interpretation is true, and we do not know. The electron may be many things at once. Then one thing when measured, it may always be one thing, with the rest being shadows. It may exist across countless realities, with us encountering only its presence in our particular branch. What is not in doubt is that something happens at the moment of measurement. The probability cloud sharpens into a single result. The wave becomes a particle, or appears to. The electron picks an outcome, or seems to. We do not know how. We do not know why. We do not know what is doing the picking, or whether there is any picking at all. A century of physics, and the electron has kept it secret. We have walked across 33 chapters through an electron that will not be pinned down. It is a wave that becomes a particle when watched. It is a probability cloud with no definite location. It rotates in a geometry that requires 2 full turns to come home. It walks through walls and crashes into nuclei mid-tunnel. It refuses to share a quantum state with another electron, holding up the entire structure of solid matter through the simple force of its no. It links with distant partners across any space, in correlations that ignore the speed of light. It carries a mass we cannot explain, a charge we cannot derive, and an existence we cannot reduce to anything more fundamental. It is also by far the best understood particle in physics. We can predict its behavior to 14 decimal places. We can build the modern world on top of it. We can manipulate it with surgical precision. The contradiction is exact. The electron is the most known and the most mysterious thing in nature at the same time. What does this tell us about the universe? It suggests that our concepts of particle, wave, location, and substance are all approximations of something deeper that we have not yet captured in language. The electron is one node in a larger reality whose true shape remains hidden. Our physics has gotten the math right. It has not gotten the picture right. We can compute, but we cannot fully imagine. It also suggests that the universe is not built out of small things. It is built out of something else, something more abstract, patterns, fields, probabilities, mathematical structures, and the things we call particles are localized excitations of these underlying entities. The electron is not a billiard ball that has always existed. It is a stable note in some cosmic instrument, a configuration that the universe is allowed to maintain, rather than an indestructible building block. It can be created from energy, destroyed by its mirror twin, smeared across space, until measured, linked to a distant partner, dressed in a cloud of virtual companions. None of these behaviors fit the picture of a tiny solid thing. The deeper reality, whatever it is, gives us electrons as one of its surface features. Our task as a species is to figure out what lies beneath. So far, we have caught only edges and corners. The Standard Model describes what the electron does in many situations. Quantum field theory describes its environment. Quantum mechanics describes its strange behaviors. None of these tell us what it is, why it has the properties it has, or what would emerge if we could probe deeper than current experiments allow. There are reasons to hope. New experiments are planned to push the precision of measurements further. New theories are being developed that try to unify the standard model with gravity, with cosmology, with deeper structures of mathematics. New particle accelerators are being designed that will probe energies and distances we have not yet reached. Each advance opens the possibility of finding something the electron has been hiding. But there are also reasons to suspect we may never reach a final answer. The deeper levels of nature may be inaccessible to physical experiment, requiring energies we cannot produce or observations we cannot make. The electron may be one face of a structure whose other faces lie in mathematical spaces our minds cannot fully visualize. We may have already gathered most of the evidence we are ever going to gather, and the remaining mystery may be a permanent feature of how nature presents itself to creatures like us. Either way, the journey is its own reward. The electron, this single particle, is a window into the strangest aspects of reality that humans have ever discovered. It is the closest thing to a magic trick that nature performs in plain view, every moment, in every atom of everything. You are made of these mysteries. Right now, in your body, 10 octillion electrons are doing all of this, interfering, tunneling, refusing to share, linking, collapsing, dressing themselves in clouds, holding the chemistry of your cells together. Every thought you have is electrons jumping between probability clouds in your neurons. Every breath is electrons forming bonds in your lungs. Every word you read is photons launched by electrons changing their orbital states, traveling to your eyes and triggering more electron transitions in your retina. You are the question that the universe has been asking itself for 13.5 billion years. The electron is the alphabet of the question. Whatever the answer is, it is being written, right now, in you.